So let's start with our first lecture on our course on design of reinforced concrete structures. Our first chapter is concrete structures and design methods, and in this chapter we will look at four different topics. First, we will look at the introduction to reinforced concrete structures. In second part, we will look at some design methods or design philosophies. We will look at what it means by characteristic strength and loads, and finally we will look at the design process and the basis for design. So let's start with the first chapter. The concrete word is derived from the Latin word concretus, and that concretus means compact or condensed. All of you must be acquainted with the subject of concrete technology, and in concrete technology you have studied that the primary ingredients of concrete include cement, aggregates and water. And aggregates can be both fine aggregates or coarse aggregates. Fine aggregates means sand and coarse aggregates means gravel. These four elements, cement, fine aggregates, coarse aggregate and water, are the primary ingredients of concrete. And besides these primary ingredient, there may be other elements. For example, the presence of admixture which perform a very specific role in the concrete. This concrete was first invented by the Romans, and that concrete that the Romans discovered is today known as simply concrete or hydraulic cement-based concrete. We also know that concrete is strong in compression but weak in tension. The tensile strength of concrete is approximately 1/10 of its compressive strength, so that concrete can withstand the compressive forces very easily. But whenever they are subjected to tensile forces, even a very small amount of tensile forces can cause cracking in the concrete. Hence, we come to the concept of reinforced concrete. Reinforced concrete means the concrete which is embedded with the steel bars. And these steel bars compensate for the concrete's inability to resist tension. So this is the general introduction to the reinforced concrete. You already know what concrete means, and reinforced concrete is the concrete that is embedded with the steel bars, so that concrete section, now we know that section is reinforced concrete section, that section is able to take or withstand the tensile forces in addition to the compressive forces also. So what is meant by design? We looked at the meaning of reinforced concrete. Now let's look at the meaning of design. So instead of looking at design separately, here I have made a table showing the differences between analysis and design. So what is analysis and what is design? Analysis means determining the response of a structure to excitations or loading, whereas design means determining the structural materials and proportioning of structural elements so that the structure can withstand the excitation or loading with an acceptable level of response. So if you suppose that we have a certain structure here, let's say this is a building structure. This building structure may be subject to different types of loadings. Those loadings may be the load due to the dead load and live load, the load due to the earthquake, or the load due to snow, or the load due to wind. This building structure can be subject to various different kinds of loading, and the action of these loadings on this structure produces certain effect on the structure itself. So the process of determining the effects of those loadings is known as the analysis. So what do we determine at the end of the analysis? We determine the response of a structure to those loadings, and these responses are calculated in the form of displacements and internal forces. You can see here the response of this building structure to these external loadings are calculated in terms of displacement and internal forces. These internal forces may be axial force, shear force, or bending moment. Whereas in design, whatever is the output of analysis, these displacement and internal forces, we take the output of the analysis process and then we use those output actions, that means this displacement, axial force, shear force, bending moment, We use this output to determine the cross-section sizes and the reinforcement. So remember that in case of reinforced concrete, design means generally we determine two different things in the design process. One is the dimensions or cross-section sizes of our various elements, and another is the amount of reinforcement that may be required in that cross-section. So design of a reinforced concrete section typically involves determining two things. One is the cross-section sizes and another is the reinforcement. And how are these things determined? These things are determined by using the analysis output. That means these displacement and internal forces. So the process of analysis is fairly general. That means the process that we use to get these load effects, that means these internal forces and this displacement, is fairly general. Whether you use any Indian code or American code, or whether what you have to understand is the mechanics is fairly general. That means there are some universal method of analysis of these sections and some universal methods of getting this displacement and the internal forces, whereas design is not general, but rather it is dependent on the code of practice. So the way to reach for these things, axial force, shear force, and bending moment in general, and the next step, that is the design step, now differs, and now design is based on the specific code of practice that you follow. For example, even if when you are designing for example a concrete beam, and you take the value of some moment in that concrete beam, using the same moment, sometimes you may get the value of reinforcement to be a little smaller, a little bit less, or you may get the value of reinforcement to be a little bit greater. That value of reinforcement or that value of design is based on the code of practice that you adopt. So this is the difference between analysis and design. If you see it, analysis precedes the design, or you can say that design succeeds the analysis. First we perform the analysis, we get the element or member actions such as displacement and internal forces, and then we use those member actions to determine the cross-section sizes and reinforcement in the case of reinforced concrete structure. So in this diagram you can see various reinforced concrete elements, and most of these concrete elements we learn to design and analyze in this course of design of reinforced concrete. For example, if you look from the very bottom, you can see that there is a spread footing in this building here, and then these spread footing, on these spread footing are resting the columns of the structure. These columns go to the first floor level, the second floor level, and to the upper heights of the building. You can also see here the slab on grade. You can see the wall footing here. You can see the foundation wall. This foundation wall is supporting or resisting the load due to swell earth pressure from this outside. Similarly, you can see the staircase. This staircase is used to go to the upper floors of the building. You can see different types of beams here. You can see joist here. You can see joist slab, and also you can see this first floor slab and second floor slab. So these are the different structural elements or different reinforced concrete elements present in our building element. And remember, since this is our course of design of reinforced concrete structures, the design is primarily focused on the reinforced concrete elements present in a building. We will always take the example of a building. We will always take the moments and the different types of forces coming onto our building, and then we will design for the different building elements. So the primary example or the primary structural system will be a building in this course. You can also use reinforced concrete elements to design other different structures such as bridges or dams or any other structure, but in this course we will be focusing on the building elements. Now let's come to these two things here: characteristic actions or characteristic loads, and then characteristic strength. So we saw the difference between analysis and design there, and when talking about the analysis, we talked that different kinds of loads may act onto our structure. Those loads may be of different types. For example, the dead loads, that means the weight of our structural elements themselves, the live load coming onto our floor systems, the earthquake, snow load or wind load or whatever load it may be. So those loads that come onto our structure, these are known as characteristic load. So how do we determine the value of the characteristic action or load? If you are designing a real life structure or real life building, you generally take the value of, or you generally take the magnitude of the required load from different codal provisions. You look at a certain part of a specific code, and based on the type of your structure or based on the uses of your building, you will take the value of the design loads. So in case if we hadn't been given those design loads in our codes, then how would we determine these characteristic loads or the characteristic action that will be coming onto our structure? We will see that here. So this characteristic load is defined as the load that shall not be exceeded by a certain accepted or pre-assigned probability during life of the structure. And this percentage is usually taken to be 5%. And for all practical purposes, the specified load in the codes is taken as the characteristic load in the absence of statistical data. Generally, we have to perform statistical analysis to get the value of characteristic load, but in cases that we do not have a vast amount of statistical data, then we can take the value of the load specified in our codes as the characteristic load. So you saw the definition here. The characteristic load may be defined as the load that shall not be exceeded by a certain accepted or pre-assigned probability, and that probability is usually taken as 5%. So if you look at the diagram on this right hand side, you see this is the diagram between the frequency of different loads on the y-axis and the value of the loads on the x-axis. And the frequency or the distribution of our loads generally is a bell-shaped distribution, that is the normal distribution. And in this normal distribution, you know that the normal distribution curve is always centered on the mean. So this is the mean value of our load. And then for 5% of probability, the error is given by this 1.65 times the standard deviation. You can get this value of 1.65 from any standard statistics textbook or from any standard statistical table, and you see that the probability of exceeding this characteristic load is less than 5%. So the 5% of the result will lie to the right hand side of this normal distribution curve here, and this point where we get the 5% of result, this point is known as the characteristic load. So in this slide, if you see, I have defined some terms here: the mean return period, the design life of the structure. So this process is generally adopted, for example, when you are calculating the probability of exceedance of certain events such as the wind event or any flood event, then in that case you calculate the probability of exceedance in this way. So if the return period of any event is R and N is the design life of the structure, then you can say that the reverse of R, that means the reciprocal of R, gives us the probability of exceedance for that event in any year. So if you want to find the probability that it will not be exceeded, then the value is given as 1 minus 1 by R. And this probability that it will not be exceeded is for 1 year or any particular year. The probability that it will not be exceeded during the whole life of the structure, that means n years, is given by 1 minus 1 by R to the power n. So if you want to find the probability that the event will be exceeded at least once in n years, the probability is given by this formula: 1 minus 1 by R whole to the power n. And this probability of exceedance, if you look at the wind code or the Indian code for wind loading, that is ISA 875, you may not know about that. In this case, the probability of exceedance, I think, is taken as 63%. So I just want to show you the method to calculate the probability of exceedance here. So we saw in our previous lecture that if we do not have any statistical data, then we take the value of the loads given in our codes as the characteristic loads or characteristic action. If we have the statistical data, then we have the formula given here. The formula to find the probability that a load may exceed the characteristic load is given by this formula here, where this phi c is the cumulative distribution function, Qm is the statistical mean of the observed maximum loads, Qc is the characteristic load, and sigma is the standard deviation of the load. So Pf means the probability that a load may exceed this value of characteristic load, that is Qc. So the value of the cumulative distribution function, that means phi c, depends on the statistical distribution of loads. And that statistical distribution is generally assumed to be a normal distribution, as we saw in the normal curve in our previous slide. So by assuming the normal distribution, now you can find the value of this mean load here, that means Qm. Now to find Qm, just rearrange this equation here. This equation 1 is rearranged and you get the equation to be Qm minus Qc by sigma is given by this phi c inverse into Pf. So suppose that phi c inverse into Pf is represented by this minus k. So the value of Qc is now given as Qm plus k sigma, where minus k means this here. So now k is a coefficient associated with the pre-assigned probability of failure. Now we know that for a characteristic load that shall not be exceeded by a probability of 5%, Pf means 5 by 100, and the k value is given by phi c inverse 0.05. So if you look at any standard table for this value of k, the Pf and Pf 0.05, the value of k is obtained as 1.65. So if you substitute the value of k here, you can get the value of characteristic load, which is given as the mean load plus 1.65 times the standard deviation. So this is the formula to find the characteristic load if you have the statistical data available. Now let's look at one example and you will be clear about this formula here. So I have taken this example from the Design of Reinforced Concrete Structure book by N. Subramaniam. Let's look at this example. An industrial building has been designed to resist a floor live load of 5 kN per meter square is given in this code here. But later on, statistical readings were taken on similar slabs and the observed live loads in kilonewton per meter square on the various slabs are given here. For example, we had 13 slabs in which we found the load to be 3.2 kN per meter square, 15 number of slabs where the load was 3.8 kN per meter square, 35 slabs with 4 kN per meter square, 10 slabs with 4.2 kN per meter square, and then another 10 slab with 4.4 kN per meter square. So we actually took the load to be 5 kN per meter square in our design, whereas when you checked for statistical data, you found these statistical data. So now you have to determine whether the characteristic load. What is the characteristic load? If the accepted probability of the load is not to exceed 5%, assuming normal distribution. So you have to determine the characteristic load here. So we are given the measured live loads here. The total number of sample is 13 plus 15 plus 35 plus 10 plus 10. Because there are total number of slabs is 83, the total number of sample is 83. To find the value of mean load, just do this. For example, 13 into 3.2 plus 15 into 3.8 plus 35 into 4 plus 10 into 4.2 plus 10 into 4.4 divided by the total number of sample, that is 83. You get the mean value to be 3.91, and then you can again use your calculators or use Excel sheet to calculate the standard deviation. You will find the standard deviation to be 0.3512. Here coefficient of variation also has been calculated. Let us ignore this for now. Now we have the mean load and we have the value of standard deviation. We can find the characteristic load. The characteristic load is given by this formula here, as we calculated in our previous slide. The mean load is 3.91 plus 1.65. This 1.65 is a factor for 5%. If it was any other percentage except this 5% here, then you have to look at statistical table and find this value. It is 1.65 into standard deviation, that is 0.3512. So our characteristic load comes out to be 4.489. And how did we get this? We got this from statistical analysis. Now see here, our characteristic load is taken, or we observed our characteristic load is 4.489 kilonewton per meter square, whereas we used a load of 5 kilonewton per meter square in our design. So the magnitude of load that we used, 5, is greater than the actual value of the characteristic load. So that means, since in design we have used a comparatively higher magnitude of load, our design is assumed to be safe. The same thing is written as conclusion in this numerical. The characteristic value that should have been used in the design is nearly equal to 4.5 kilonewton per meter square. This should have been used in design, whereas we have used a higher value, that is a value of 5. Hence, our design is safe. So this is how you calculate characteristic load. And now characteristic strength. The definition is the same. That means characteristic strength, if you look at the definition of characteristic load, it says that the load that shall not be exceeded by a certain percentage, that means 5% during the life of the structure. Similarly, characteristic strength means that strength of the material which is not exceeded by more than 5% of all the samples during the life of the structure. So variability in quality control causes variability in the strength of concrete. Experimental studies have revealed that the probability distribution of concrete strength is approximately normal. That means it follows the bell curve or the normal curve, the same curve that we saw previously for our characteristic loads. So to find the characteristic compressive strength, table 11 is given in IS 456 code. I will discuss about the IS 456 code in our next lecture perhaps, because that will be the code of practice that we adopt in this design course here. So just I want to point out is that table 11 of IS 456 code gives us the characteristic compressive strength compliance requirement. So previously for concrete below YUM20 grade, that means for YUM15 grade, there was a separate criteria for characteristic compressive strength, and for other grades of concrete, that is YUM20 or above, there was a separate criteria. So this is the old table here. One of the recent amendment in IS 456 code has changed that table, and now the criteria is same for all grades of concrete, whether they are YUM15 or YUM20 or above. The criteria is the same. So whenever you perform a cube compressive strength test, each individual test result, the value of each individual test result should be greater than or equal to the characteristic strength minus 3 Newton per mm square. Whereas if you find the mean of the group of 4 non-overlapping consecutive test results, then the value should be either greater than or equal to FCK plus 0.825 times the standard deviation, or FCK plus 3 Newton per millimeter square, whichever is greater. So for a group of 4 non-overlapping consecutive tests, that means, for example, if you have performed there 5, 6, 7, 8, if you have performed there 8 samples of, if you have here 8 test specimens, then you have to calculate the mean of 4 non-overlapping consecutive tests. That means first mean of these 4, then mean of these 4, and again these 4, and again these 4. So in this case, the mean of the group should be either greater than or equal to this value or this value, whichever is greater. Individual result should be greater than or equal to FCK minus 3, whereas for group result either this or this. So FCK, you will have the characteristic compressive strength. For example, for M20 grade, FCK is taken as 20 Newton per millimeter square. But how do you calculate this standard deviation here? What the code says in note is that in the absence of established value of standard deviation, the values given in table 8 may be assumed. That means table 8 of the same code gives us the assumed standard deviation for different grades of concrete. For example, for M10 and M15 it is 3.5, for M20 and M25 it is 4, and for these other grades it is 5. So these values of standard deviation should be used when you have not performed at least 30 samples. If you have performed test in less than 30 samples, then you have to use these values of standard deviation. But if now the samples number exceeds 30, then you have to calculate the standard deviation from the test result values that you have got from these 30 samples, and then you have to use that standard deviation here. So remember, for up to 30 samples, you can use the assumed standard deviation given in table 8. For more than 30 samples, you have to derive or you have to establish the value of standard deviation by performing calculations yourself and use that value of standard deviation here. So this is about characteristic strength and characteristic loads. Now, two topics are remained in this first lecture or first chapter of our design course here. One is the design process and design basis, and another is the design methods or design philosophies. So we will continue with the design process or design basis in our next class. I would like to stop here for today's lecture. In next class, we will see about the design process. We will see at some charts, and then we will see some design methods or philosophies. We will discuss about the working stress method, the ultimate strength method, and the limit state method. So these two topics I will leave it for our next lecture. Till then, stay safe and see you soon. Thank you.